Welcome back. Section 6.1 Definition and examples of linear transformation. Definition. Let V and W be vector spaces. A function L from V to W is called a linear transformation of V onto W if L of U plus V is LU plus LV for every pair of vectors UV from V. This means L respects addition. It takes addition of vectors and gives you addition of their images. Second condition, L of C times U. This is scalar multiplication. The scalar comes out. That means L respects scalar multiplication. This happens for every real number C and every vector U. If V and W are equal, that is L goes from V to V, it is called a linear operator on V. Theorem. Let V and W be vector spaces. A function L from V to W is called a linear transformation if and only if this one condition needs to be checked. L of AU plus BV is ALU plus BLV for all real numbers AB and all vectors UV. Okay? Onward. This is an if and only if statement, so onward. Suppose L is from V to W is a linear transformation. Consider L of AU plus BV. Now notice L respects vector addition, that is part A of the definition, so it splits along the vector addition. L of AU plus BV is L of AU plus L of BV. Further, L respects scalar multiplication, so the scalar can come out in each case, which is exactly what you want. Reverse direction. Suppose L of AU plus BV is ALU plus BLV for all real numbers AB and all vectors U. You want to show that L is a linear transformation. Well, to prove A, that is L respects vector addition, take any two vectors U and V. L of U plus V is L of 1U plus 1V. Okay, U is 1U, V is 1V. But L splits along plus and scalar multiplication, so it splits along this plus and the scalar multiples come out. But 1 times LU is LU, 1 times LV is LV. In other words, L of U plus V is LU plus LV. That is, L respects vector addition. Moreover, to prove the part where L respects scalar multiplication, multiply by C for any vector U. I can also think of it as 0 times any vector V. It doesn't have to be some other V. It could be U. Now, by assumption, you are going to get the scalars out. So, CLU plus 0LV. 0LV is nothing, 0. So, you get LCU is CLU. That means L respects scalar multiplication. It respects scalar vector addition and scalar multiplication. So, L is a linear transformation. Here is an example. Suppose you have a matrix, M by N matrix. Take any vector which is a column of size n. You see, A is M by N, V is a column of size n, that is, V is n by 1. So I can multiply on the right by V. AV, M by N and N by 1, this result will be M by 1. So you can define a function L from Rn to Rm. Rn is for V, Rm is for the result. How do you define L? Well, L of vector V is take the matrix multiply by V. Correct? So This is a function because multiplication by something is a well-defined output. So L from Rn to Rm is a function. Moreover, suppose you have two vectors v1 and v2 in Rn, then L of v1 plus v2. L, we have defined it as multiplication by A. So it is A times v1 plus v2, which is AV1 plus AV2. AV1 is LV1, AV2 is LV2. So what happened here? If you remember, matrix multiplication distributes. So you have L of V1 plus V2 equals LV1 plus LV2. That is L respects vector addition. Now take any real number C and any vector V. Then what is L of CV? L is nothing but multiplication by matrix A. Matrix A, if you remember, it takes scalars out. So CAV. AV is LV, so C is outside. In other words, L respected multiplication by scalar. It came out. That is, it respects scalar multiplication, it respects vector addition. So L is indeed a linear transformation. So this is an important example. Given a matrix, you get an automatic linear transformation, which is nothing but multiplication by matrix. Now let's list out several examples of linear transformations. One is reflection with respect to the x-axis. So suppose you think of vector AB as a point in coordinate plane. So a reflection about the x-axis means the y-coordinate or the second coordinate changes sign. First coordinate is the same, second coordinate changes sign. This is reflection. You can check that it satisfies vector addition, it satisfies scalar multiplication. This is a linear transformation. Likewise, reflection with respect to the y-axis. Again, think of the R2 as coordinate plane with two coordinates A and B. You are reflecting about the y-axis, that is, positive x becomes negative, negative x becomes positive. So the first coordinate changes sign. Second coordinate, there is no change. This is reflection with respect to y-axis. You can check such an L will respect vector addition and scalar multiplication. That is, it is a linear transformation. What about projection? From 3 dimension to 2 dimension. So think of this as x coordinate, y coordinate, z coordinate. You forget the z coordinate. Take x and y coordinate, map it to x and y coordinate. Z coordinate is forgotten. This is called projection from 3 dimensions to 2 dimension. So for any 3 vector, that is a vector with 3 entries, you get a vector with 2 entries. This L respects vector addition and scalar multiplication. Easy to check. Dilation. Dilation is nothing but scaling up. Be it 3 dimension, n dimension, 2 dimension, definition is the same. L from R3 to R3, define it as take a vector ABC, multiply it by scalar R for some fixed R greater than 1. When R is greater than 1, your vector entries become larger. Hence the name dilation. This is a linear transformation. Likewise, contraction. When you scale down, here again I am using example of R3. It can be any Rn to Rn. You are multiplying vector ABC with scalar R. So you get RA, RB, RC, where R is between 0 and 1. So think of R as, I don't know, 0.2, 0.5. When you multiply by 0.5, your entries become smaller. Hence the name contraction. This is also a linear transformation. Rotation counterclockwise through an angle theta. Suppose L is from R2 to R2. So we are looking at coordinate plane R2 to R2. You are defining L by multiplication by this particular matrix. If you remember, we just saw multiplication by a matrix is a linear transformation. In particular, multiplying by this particular matrix, it is actually rotation counterclockwise. Okay. Now here is some other concrete example. From R3 to R3, ABC is being mapped to A plus 2B, B minus 2C, A plus C. This is just a formula. Let us check whether it is a linear transformation. Well, it is a function because every vector gives you a unique output given by this formula. There is no ambiguity. So L is a function. Now suppose you have two vectors A1, B1, C1, A2, B2, C2. You add them up, apply L. So L of A1, B1, C1 plus A2, B2, C2 is equals L of A1 plus A2, B1 plus B2, C1 plus C2. Now apply this formula. First coordinate plus 2 times second coordinate. First coordinate plus 2 times second coordinate. Second entry, second coordinate minus 2 times third coordinate. Second coordinate minus 2 times third coordinate. Third entry, first coordinate plus third coordinate. First coordinate plus third coordinate. Okay, so this is the result. On the other hand, what is L of A1, B1, C1 plus L of A2, B2, C2? Apply the same formula. You get first coordinate plus 2 times second coordinate. Second coordinate minus 2 times third coordinate. First coordinate plus third coordinate. Apply the same formula here. You get this. Now look at this carefully. If I add these two, don't I get this? Add these two, don't I get this? Add these two, don't I get this? Indeed we do. So you have L of A1, B1, C1 plus A2, B2, C2 is L of A1, B1, C1 plus L of A2, B2, C2. That is L respects vector addition. Now let's try scalar multiplication. Multiply by a scalar, apply L to it. First coordinate plus 2 times second coordinate. Second coordinate minus 2 times third coordinate. First coordinate plus third coordinate. Okay, we have applied the same formula. Now try L of ABC and then multiply to R. Well, you have your formula, multiply by R, note multiplication distributes, and you get the same output. In other words, L respects scalar multiplication. Therefore, L is a linear transformation. Here is a case where you are a non-example. Suppose L is from R2 to R2 given by L of AB is A plus B, B squared. Why is it not a example of linear transformation? Let's check. First, it is indeed a function. The output is well defined. There is no plus minus, none of that. A plus B is a proper number. B squared is a proper number. L is a good enough function. Now let's try addition. L of A1 plus B1 plus A2 B2. Add these two and then apply the formula. Formula says first coordinate plus second coordinate and then second coordinate squared. Good. What about individual cases? L of A1 B1 plus L of A2 B2. L of A1 B1 first plus second coordinate and then second coordinate squared from here. Likewise from here, first plus second coordinate squared. Now if I add these two, what do I get? First coordinate is good, it agrees here, but second coordinate is not good. We know that B1 squared plus B2 squared is not B1 plus B2 quantity squared. Because you see, quantity squared, you have an actual formula. So it does not respect vector addition, It is not a linear transformation. Let's continue next video.